Before we begin talking about coordination chemistry, just a brief review of topics from last time. Surface states are very important to quantum dot science. Any semiconductor with band gap and particle in a box like states that you see in the absorption spectrum is very likely to have surface states derived from atoms that make fewer connections than those on the interior. And those fewer connections mean that the orbital splitting is smaller and the product orbital is closer to the parent atomic orbital. So you can see those diagrammed. Here on the left, this surface cadmium derived orbital is close to the parent 5s and below all the empty orbitals associated with the valence band, with the conduction band. Now, this is one of many different types of surface derived orbitals, some of which will be delocalized into the bands. So only some of these really will fall below the band edge of the convalence band. And likewise on the selenium side, surface selenium atoms are going to have lone pairs that some of which will fall into the optical gap that is derived by the HOMO-LUMO transition. In any case, most nanocrystals, their excited state lifetime and their recombination kinetics and whether they do charge transfer outside of the crystal to dioxygen or some other kind of acceptor is all controlled by surface chemistry. And so, promoting this electron into the conduction band, now the electron has this choice of whether it's going to head to a surface cadmium atom or recombine radiatively. And likewise, the hole has a choice. So a selenium derived lone pair from a surface selenium state can trap the hole. And so that makes the surface chemistry and the number of and types of dangling bonds that you find on a surface really important to semiconductor science, very broadly speaking, but especially to nanocrystals because the surface area to volume ratios are very high when you're below 10 nanometers or so. Okay, so things like the photoluminescence quantum yield, which is really important for quantum dots of the type we've been discussing mostly, and also the charge separating ability, very, very sensitive to surface structure. And we talked about how this can give rise to blinking. This is a proposal more than a certainty that a trapping of a hole gives rise to this hole localized on the surface, and then a trion in the interior of the crystal that lives for a long time. And that trion, as we discussed, does Auger recombination very effectively. Auger recombination being much faster than radiative recombination in most cases. And so that trion doesn't recombine radiatively for the most part. And then when the charges recombine and arrive at the neutral starting state, then you get something that's luminescent again. So the nanocrystal quantum dot undergoes photoluminescence. It does trapping of some kind by ionization or some kind of a surface state. The product trion is dark relative to the on state, and then somehow it neutralizes and returns to its original charge state and suddenly turns on again, and this gives rise to photoluminescence, intermittency, or blinking. Okay, so the quantum yield in the photoluminescence quantum yield in a quantum dot strongly dependent on the surface chemistry of the sample. Surface chemistry of the sample will play a big role in these kinds of blinking traces. Okay, so how does that work exactly? So we're going to talk about ligand coordination today. And I've diagrammed what happens when an amine ligand, sort of prototypical ligand for a colloidal nanocrystal, coordinates the surface. The amine is a donor and brings an electron pair to the surface, and it binds to an empty orbital, and that's going to be a cadmium-derived orbital on the surface. And that connection leads to an orbital splitting, just like in any other orbital interaction. And so the acidic cadmium ion stabilizes the electron pair on the amine ligand, and the basic donor amine destabilizes the surface cadmium. So in other words, after the amine is bound to that surface cadmium, it's much harder to put another electron pair there. And once the amine and the cadmium bind to one another, it's much harder to pull an electron off the amine. That's why you get this splitting, or a way to interpret the splitting. So by binding an amine to the surface cadmium ion, you can modulate the energy of these surface-derived states. So here we've modulated the energy of the cadmium-derived state, and that would change the probability of electron trapping. And this is a commonly observed theme in this area. Ligand coordination has a really big impact on photoluminescence, okay? I promise this is far more complicated than we understand and have time to talk about, but qualitatively speaking, electronic structure of these types of materials is very heavily dependent on ligands, and recombination is very heavily dependent on ligands. Okay, so ligands are very important to electronic properties. Okay, so let's talk briefly just about some questions of interest and that we would like to understand better. Things like, what determines ligand binding strength? Is one type of a ligand stronger than another, and why? And for transition metal chemistry or small molecule chemistry, this kind of stuff is well understood. Roughly speaking, it's an acid-base type of an interaction. The stronger the donor, the better the binding. There are hard-soft matching principles to worry about, and of course, sterics. But in nanocrystal quantum dots, I would say this is not very well understood because it's difficult to study ligand binding strength in these kinds of materials. And we'll talk about a few examples, mostly from my group, where we have attempted to do this kind of thing. And then, another good question is, how does the binding of ligands influence the energy of the crystal as a whole? Okay, and how does that relate to crystal formation? And we're going to talk about that, not this time, but next time, using some of what we learned today to address that question later. Okay, and then as I talked about on the previous slide, how does this binding influence recombination, and what does it do to influence these trap states, or in some cases induce them? All right, so more broadly speaking, coordination chemistry of particles is essential to applications. So if you want to make a photovoltaic device, most most nanocrystals are synthesized with organic ligands binding their surfaces that make them soluble or dispersible in organic solution. But photovoltaic devices made out of organic material tend not to be very effective because of charge transport limitations. So if you want charges to hop from particle to particle in your device, you don't want a bunch of organic stuff in the way, because organic material does not conduct as well as inorganic material for the most part. Okay. Another is that people often take quantum dots or metal particles or oxides, and they want to put them in some kind of a new environment for the application of interest, like labeling of tissue is one good example. There, the particle has got to be soluble in water, and it also has to kind of tag targets of interest. If you're trying to attach a particle to a cancer tissue to help eliminate the cancer tissue or to image it, then you need some way to attach it. And so the exchange of the ligands bound to the surface and the ability to anchor tags is a very, very important challenge. And because of the interaction between these ligand exchange reactions and the the electronic structure of the particle, designing exchange methods is a challenge. You not only have to achieve the new function, say good charge transport or water solubility, you also have to preserve the electronic property of interest in that material. Okay, and as I mentioned, it's difficult to study these kinds of exchange reactions, and it's very difficult to know how or why ligands impact recombination the way they do. So, very important topic, deserving of a lot of research. So I'm going to just introduce briefly here a couple of different ligand classes that we're going to discuss today. And I've labeled them charge neutral lipophilic, electrostatic stabilization hydrophilic, and electrostatic stabilization lipophilic. Most of the nanocrystals that my group works with are soluble in organic solution. They have ligands bound to them, like amines and thiols, or metal carboxylate or thiolate complexes, or phosphonates are a good one. And they have these organic tails that hang off the surface and that make the particles soluble in hydrocarbon solution. Another, perhaps even more important class of ligands are ions that are adsorbed to the surface. Metal ions that bind to the outside of the particle and have some counteranion in solution, or vice versa, some sort of ammonium X salt, say ammonium sulfide, where the sulfide adsorbs in a basic type of a way, and the ammonium countercation floats in the polar medium. And this charge separation and sort of net charge concentration on the particle surface keeps the particles apart from each other. If the particles on average have a positive charge close to the surface, two positively charged particles won't get very close. And this is very common in colloid chemistry. It's probably the number one way that colloids are stabilized, especially big polarizable colloids like metal particles of gold, for example. And then the last one is another class where the ions that are adsorbing are actually lipophilic. So, you can have a long aliphatic chain with a counterion at one of its tails, and that counterion could be electrostatically attracted to a particle with a net charge, overall giving you a charge neutral complex. All of these structures are meant to be charge neutral. But on the bottom there, the counterion is now organic and lipophilic, and so that ion pair in that salt, that particle, which has all this electrostatic stuff going on at the surface, might be soluble in toluene, for example. Okay, all of these are important and have their own, deserve their own lectures. So, just briefly about electrostatic stabilization, there is an awful lot of literature on this topic, especially in the soft matter literature. Quite a bit of work has been done understanding the electrostatic arrangement. So take a look there at the Gouy-Chapman model of the arrangement of ions around a particle. So these particles have a net negative charge right at the surface. You can see I've drawn all these negative charges immediately adjacent to the particle. And then various associated cations and anions kind of evolving in a gradient as you move away from the particle surface. And various people have studied the electric potential, because you have a field that develops when you have net negative charge very close, concentrated at the surface, that then diffuses or dissipates and becomes a net positive charge as you move away from the particle. A lot of people have looked at that relationship and how that influences colloidal dispersibility, among other things. And so a couple of important parameters to be aware of. There's the potential right at the surface where you have the excess negative charge. And then there's adjacent strongly bound ions that attach directly or are very strongly associated with those surface negative charges. And that the strongly bound type are sort of what fall within what's called a Stern layer. And then as you move further away from the particle, you get away, and the charges become less and less tightly bound, you start approaching what's called the slipping plane. Slipping plane helps you understand how this object moves in solution. So the particle with all of its associated ions diffuses in the medium, and it carries with it some fraction of those ions and the solvent that is associated with them. And so if you look at the size of the object as it's moving, you have to include some of that solvent and some of those associated ions to really understand how large it appears, and that the slipping plane defines those things that move with the particle, as it diffuses through solution. Um, there's also something called the zeta potential, which is the electric potential associated with that slipping plane. So there's a certain amount of charge, net charge within the slipping plane. And so you can think about that crystal as it moves as being positive or negative. In this case, it would be a negatively charged crystal because of the concentration of negative charge at the surface. And the zeta potential is the electric potential associated with that net negative charge at the slipping plane. Okay, and then as you go further and further away, eventually you get to a charge neutral situation where the concentration of ions becomes the equilibrium concentration in solution, and there's no more, the electric potential has dissipated to zero, and that is the electric double layer thickness. Okay, so zeta potential in particular is a really important principle in this because it sort of defines how colloidally stable the dispersion is. As you let the particles get closer and closer together, they experience a type of a van der Waals attraction, and they at the same time experience an electric repulsion, okay, because of this charge concentration. And there's quite a bit of work on this to understand the properties of these colloidal dispersions and their stabilities. And the sort of a simple or early implementation of this sort of thinking is called DLVO theory, after the authors shown there at the top. And it's really just a potential that determines the sum of these two forces, the van der Waals force and the electric repulsive force. Okay, and so the van der Waals force can be approximated this way. Van der Waals forces are more complicated than this, but they boil down to this type of an arrangement here, where A is this thing, the Hamaker constant, and the Hamaker constant is sort of a fundamental property of a material, and it defines how attracted two particles can be to one another, and it's very related to polarizability. So metals, for instance, will have a high Hamaker constant, and things like plastic will have a low Hamaker constant. Okay, there's also the size to consider, and then you can measure this van der Waals attractive potential as a function of the separation between the particles. The closer they get, the more tightly they are attracted, or the more strongly they are attracted to one another. Now, there's also the electric repulsive potential, which is a slightly more complicated potential, but it's related to the dielectric constant of the medium, the separation between the particles, and then this zeta potential squared. So zeta potential, again, remember, is this concentration of charge or electric potential within the slipping plane. Okay, and this is also exponentially dependent on the electric double layer length. Now, the double layer length, and this is the total distance over which the electric potential decays to zero. That parameter is actually influenced by ionic strength. Okay, and so if you increase salt in the solution, for example, the concentration of salt helps the charges to diffuse or the excess charge to dissipate more rapidly. And there's an exponential relationship there between that double layer length and this repulsive potential. So zeta potential helps you understand how repulsive the particles are to one another. as does this electric double layer length, which I mentioned is determined by ionic strength. So as you push the particles together, this electrostatic repulsion increases with the radius, and the van der Waals force increases uh, 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 with radius. And it turns out that the sum of these two quantities reaches the minimum down here until the particles actually physically get within what's called this potential barrier, where they then dissipate, or where this thing then falls off of a cliff. And so it turns out that there's kind of a characteristic minimum here, um, where the two are sort of stably bound to one another. This is a relatively weak binding. They're easily dissociated, but there is kind of um, a local minimum. Okay, so electrostatic potential defines how quickly this repulsion happens to the second power, and so maintaining a high zeta potential is very important for colloidal stability in these kinds of materials. Maintaining a low ionic strength also leads to colloidal stability for reasons related to the double layer, as I mentioned. And so people have tried to define this in sort of a qualitative sense, and shown here are these sort of ranges of zeta potential that and the uh, relative stability of the colloid. So you want zeta potentials greater than 50 or 40 in order to maintain a good electrostatic repulsion and good colloidal dispersion in this type of a system. Zeta potential is measured a variety of ways. I'm not going to go into it, but some of you will be aware that there are light scattering tools available in the Shared Materials Research Characterization Facility that measures the mobility of charged particles in an electric field, an oscillating electric field, and can extract this zeta potential value. So quite a bit of work on that in the literature. Okay, so just to sort of drive this home, I've shown you this same potential again, the total attractive and repulsive potentials plotted here. This is the repulsive one, this is the attractive one, and there's this barrier to aggregation. And the barrier to aggregation is sensitive to the salt concentration. Okay, so if you modify the salt concentration, you double it, you triple it, what you'll find is that the barrier to aggregation, where the particles get close enough to irreversibly stick to each other, goes down. And so a very common trick with an electrostatically stabilized colloid is to add salt to induce aggregation, where the particles suddenly all stick to one another and you get big aggregates that then settle out of solution. Okay, so adding salt helps separate electrostatically stabilized colloids from solution. Another somewhat surprising result is that the particle radius is actually an important parameter in determining colloidal stability. In an electrostatically stabilized situation, larger particles tend to be more colloidally stable than smaller ones. Why does this look backwards to me all of a sudden? I'm afraid I've mislabeled this. I'm gonna have to go check in on this. But larger particles, which is somewhat counterintuitive, can be more colloidally stable in this type of regime. And what you'll find is that most of the very large inorganic particles that are stabilized and handled in colloidal dispersions tend to be electrostatically stabilized, perhaps for this reason. Okay, so we're going to change gears now and talk about steric stabilization. And there's quite a deep literature on the stabilization of dispersions using polymers and polymer chains of different lengths. And I'm not going to talk about that. That's probably something you would learn about in the chemical engineering department. So instead, I'm going to talk about small molecule ligand binding. And I've just put up a sort of classical example of a topo molecule bound to a cadmium selenide quantum dot. And I've done this to try and help you understand that coordination chemistry of ligands to particles is a growing field with not, with all kinds of opportunity for fundamental discovery. So for years, people focused on the binding of neutral organic ligands to the underlying particle. And you can see in this drawing just a big orange sphere with no specification about the nature of the types of atoms, or maybe the ratio of the atoms, or the charge of the particle. But instead, one just thinks, okay, we have a neutral ligand of phosphine oxide binding a neutral particle and a neutral ligand complex overall. Okay, and so that picture permeates the literature on nanocrystal science, and it's sort of the base assumption that everybody makes when thinking about nanocrystal formulas. Um, Even for things like phosphonic acids, where you have ionizable hydrogens, for a long time it was thought that these things bind in a neutral fashion to an underlying neutral crystal. And it turns out that that is actually, this type of a binding is relatively um, unimportant compared to binding that involves uh, charge balancing or charged ligands and charged particles. So I'm going to introduce you to a method of counting electrons that helps you to think about charge balance in these types of systems. On the left, we have um, a metal-rich nanocrystal formula. So the example here is cadmium selenide. And I've used green circles to represent cadmium and red circles to represent selenium. And then this empty circle here, the white circle with the black edge, to represent a pure cadmium selenide crystal with a 1-to-1 cadmium to selenium stoichiometry. And so this cartoon on the left here shows you a cad selenide particle with 6 cadmium 2 plus ions bound to the surface of that particle. And then for each 2 plus ion, you actually have a ligand anion, where X is, say, a thiolate, a chloride, a carboxylate, or a phosphonate. And the result here is that this ligand nanocrystal complex is a neutral object. It's rich in cadmium 2 plus ions, and their charge is balanced by ligand anions, and overall you have a neutral chemical formula. So this is an alternative to the model I talked about previously, which is the neutral crystal and neutral ligand picture. So here we have a stoichiometric piece of cad selenide, an equal number of cadmiums and seleniums displayed on its surface, overall a charged neutral object here in the center, and then each of these ligands surrounding it are charged neutral ligands, denoted by an L and denoted by an X in this case. Those could be thiols or carboxylic acids or phosphine oxides, for example. And the only difference between X and L here is whether the hydrogen is along. So we have carboxylic acid and carboxylate, thiol and thiolate. And so these are sort of 2 poles of the charge balance in the nanocrystal ligand complex, and how it depends upon the underlying stoichiometry. I'll introduce briefly this XLZ ligand formulation introduced by Malcolm Green and also Jed Parkin in our department. So you can think about covalent bonds as involving the pairing of electrons. Say in this example, we have an ammonia molecule that's made up of a nitrogen with 5 valence electrons and hydrogen with 1 valence electron each, and they pair up, and that combination of electrons gives rise to what are called X-type interactions. And X-type interactions are where the ligand, in this case a hydrogen, is the ligand for the nitrogen. The ligand contributes 1 electron to the bond. Okay, this picture of ammonia is maybe a little bit counterintuitive. You don't, maybe you think about it as N3 minus and hydrogen plus or something. But in this formulation or formalism, you want to think about the fragments as neutral objects for the purposes of counting charges. So likewise, if you think about something other than covalent bond, you can also have dative bonds, where you have, say, an ammonia molecule that binds borane, similar to ammonia, except that it only has 3 valence electrons. Boron only contributes 3 valence electrons, so there's actually an empty orbital on boron. And here, the ammonia lone pair donates to the boron, and you end up with this nitrogen-boron bond, which can be depicted this way, showing formal charges, or can be depicted this way without formal charges. In either case, the ammonia contributes 2 electrons to the bond, and the boron contributes 0. And so you can say that the nitrogen is an L-type ligand, which contributes 2 electrons to the boron. And you can say that the boron is a Z-type ligand, where it contributes no electrons to the bond. Okay, so XLZ names the number of electrons in the neutral fragment that are contributed to forming a bond. And it's really useful for counting the number of valence electrons in a transition metal complex, and also for talking about nanocrystals. So here are a series of different ligand types, ligand classifications for nanocrystals that we're going to discuss. And you can see 2 different types of X-type ligands, an L-type and a Z-type. And underneath, the number of green and red balls is meant to achieve neutral formulas overall for these ligand types. So we've already talked about X-type ligands that contribute 1 electron as a neutral fragment to forming a bond with an underlying metal 2+, say cadmium or lead or something like that. And then there are also X-type ligands that balance charge with some outer sphere cation. We'll talk about some examples like that. So here we have an ion pair that's adsorbing, and there's no excess metal ion in this underlying crystal required. All the charge balances with an outer sphere cation. And then there's also the neutral donor type, phosphine, amine, phosphine oxide, thiol. And then finally, what we call Z-type ligands, these metal X complexes. So really what's drawn in this dotted box here is the same as this pair of X-type ligands in this green sphere. It's just depicted with a straight line coming off of the red sulfur or selenium atom beneath. Okay, and the reason that this type is specified is not just for pedagogical completeness, but also because metal ion ligand complexes adsorb and desorb reversibly in the chemistry of these materials. So a couple of different ligand classes, we're going to talk about each today. And in general, the pictures that my group draws to represent the chemistry you're going to see are these cartoons where the number of X's and L's and the underlying metal atoms shown give rise to charge neutral formulas. And it's just a graphical way of representing empirical formula for the material to help teach the kinds of chemistry that interests us. You could also write out formulas like these to capture those same details, but we like pictures. So an important discovery really in this area was the realization that many nanocrystals do not have a simple formula, but actually are enriched in either metal or chalcogen ions. And in this particular example of lead selenide, what you'll find is that the composition is lead enriched, and that the amount of lead enrichment depends upon the diameter. So here is plotted from 10 to 2 nanometers. The lead to chalcogen ratio goes from near 1 all the way up to 3. And this curvature suggests that the increase in the metal enrichment is on the surface of the particle. So this was kind of one of the early demonstrations that metal ions are enriched in these particles, and that this metal ion enrichment was size dependent. And I think this paper by Zager-Hens is really a very, very important discovery. I don't know how many times it's been cited, but it's really influenced the way people think about these materials. So I'm going to show you some examples of that type of enrichment and the corresponding ligand charge balance here in the subsequent slides. And I'm just going to show you for one example how you would go about studying this issue. So here's a synthesis of cadmium selenide made from cadmium carboxylate and selenium dioxide. We'll talk about the mechanism of this reaction next time. And basically, you heat these things up and you get wonderful nanocrystals that have a cadmium-enriched formula that balances charge with ligand anions. And you can make quite a bit of this kind of a sample. After purification, if you make a stock solution out of it, you can measure the concentration of ligands and semiconductor in that stock solution using absorption spectroscopy and NMR spectroscopy. And we'll talk about how exactly that works, but just briefly, I'll say that the absorbance of that stock solution is proportional to the amount of material. The NMR spectrum, also the concentration of ligands, can be measured versus an internal standard like this internal standard here, and compared to all of these signals that correspond to these surface carboxylates. So once you know the ratio, you can calculate the empirical formula of the material. And if you know how big the particles are, you can calculate how many ligands per nanometer squared of surface area. And that matches the elemental composition that you might expect for a formula of the kind depicted here. Okay, so briefly, I'll mention NMR spectroscopy and how it works in these kinds of this kind of material system. You'll notice the ligands here have these nice broad resonances, whereas this internal standard is a small molecule and has a very sharp resonance, typical of NMR of small molecules. Now, the difference is actually quite powerful. It allows you to study a collection of nanoparticles and ligands and determine whether or not ligands are bound. Okay, and so a lot of effort has been put into understanding that phenomenon, and in particular, understanding the origin of the line width. So you can imagine that this resonance out here, which is actually associated with an alkene of this oleic acid fragment, those alkenyl hydrogens have a particular width associated with them, but it turns out the majority of the width that you see in the spectrum is actually heterogeneous broadening, meaning many different environments for the alkene, rather than an intrinsic width associated with those hydrogens. And that heterogeneity actually largely derives from different degrees of solvation. The particles are not totally uniform in their ligand packing, and places where the solvent penetrates better or worse show up at slightly different chemical shifts. And so the sum of those solvation environments gives you this broad peak. And if you take ligands like this one here, this ethylene oxide oligomer, all these different hydrogens have slightly different chemical shifts. And if you look at them in different solvent media, so for example, toluene D8, methanol, and water, there's really big changes in the line width. Down here in the toluene D8 case, you see a really broad range of solvent environments for these ligands, for all these hydrogens, whereas in water, the penetration is more or less uniform, and the peak widths are much narrower. Nothing like the small molecule not bound to the particle, but in any case, clearly dependent on the solvation environment demonstrated in this type of an experiment. So the breadth somehow reflects changes in the solvation. And nonetheless, it allows you to distinguish, say, this sharp peak, which is from something free in solution, not bound to a particle, from these broad resonances that are coordinated. Another one here. This is a solvent impurity, and very sharp small molecule versus broad for bound to the surface. Okay, so we can exploit that to study things like ligand displacement reactions. Here is an example of one. This was a demonstration by Nick Anderson, a member of my group from years ago, one of my first students. Nick used tetramethyl diamine to displace cadmium carboxylate from particle surfaces. And he found that this adsorption of cadmium carboxylate, or adsorption desorption process, was actually quasi-equilibrium reaction that was fast and reversible near room temperature. And so what you're seeing here is the cadmium ions in excess being stripped off with their ligand anions and forming this complex in solution. And what Nick found was that by stripping off all those cadmium ions and their associated carboxylates, the photoluminescence quantum yield would fall off very rapidly. So Nick isolated all these materials, looked at their coverages of cadmium carboxylate, and found that the less he had, the darker the particles became, and that was reversible. He could put cadmium carboxylate back on and recover that. And so this was a very clear and quantitative demonstration showing the dependence of the photoluminescence quantum yield on coverage that is related to the charge trapping phenomena that I told you about earlier. Okay. More broadly speaking, this kind of relationship between ligand binding and quantum yield has been published many times over. Many people have observed that the quantum yield is sensitive, and generally speaking, higher coverage of ligands gives higher quantum yield. Um, um, Not always, but in many cases, that's been shown to be true. Nick's case was just a little more quantitative, but very interesting. You can see the photoluminescence drops off very suddenly at this concentration. And also another thing to bear in mind here is that this binding is rapid and desorption is rapid and reversible. And so the equilibrium that you obtain is very sensitive to the solvent conditions and whether there are any other ligands present in the solution, total concentration. And so the photoluminescence quantum yield of these types of materials is not very stable. It's very sensitive to the environment in which you're handling the material. Now, quite a bit of work was spent showing that this cadmium carboxylate desorption uncover surface selenium atoms. So cadmium carboxylate is a Z-type ligand. It's an acceptor. And the acceptor orbital stabilizes the surface selenium lone pair to which it binds. Selenium becomes the donor to the empty cadmium, and the Lewis acidic cadmium stabilizes the electron pair, pulling it out of the band gap of the crystal and preventing hole trapping from happening. And in a slightly more detailed picture, it turns out that selenium atoms that only make two connections to the underlying crystal are very important players in this type of a mechanism, because a p orbital that is orthogonal to the two adjacent cadmium atoms is non-bonding. And as a result, it falls in the middle of the gap, much like this cartoon shows. And so cadmium ion binding to those surface selenium atoms is a very important source of this photoluminescence variation with ligand coverage. Now, Nick went on to study this equilibrium and how it depends on the type of ligand that's used to displace the cadmium carboxylate. And he found some sort of somewhat predictable trends. One is that relatively weak bases like THF and methyl acetate, nitriles, these types of ligands do not displace cadmium very well, but things like amines and phosphines, they do. But within the same trend, and so I should say actually that this was studied by looking at the NMR spectrum. So actually it's this peak here, these vinylic hydrogens near 6 ppm, he added varying amounts of these molecules and then looked at the extent to which that signal sharpens. So here at the shoulder is the free vinylic hydrogen of some displaced cadmium oleate in the presence of this donor. And as you go to the right, the amount of this species free in solution increases, and correspondingly, the amount of the broad signal corresponding to ligands bound to the particle decreases. So you can pretty clearly see qualitatively the relative ordering of the displacement potency of these molecules. And something we're going to keep talking about here that pops out of this trend is the degree to which steric effects are really important. So notice, for example, tributylamine and N-butylamine are totally different. Very little displaced cadmium in this case, a lot of displaced cadmium in this case, and even just swapping butyls for methyls has a big impact on the displacement potency. Another very interesting one is that phosphorus is better than nitrogen, and that's a result of the hard-soft match. So cadmium is polarizable; it prefers a more polarizable donor, like a phosphorus. Instead of a nitrogen. A different metal ion will have different preferences. Zinc, for example, is less polarizable than cadmium, and so probably prefers harder ligands to a greater extent. And then this interesting result here, pyridine turns out to be very good at this reaction. And we think that's the case because it's flat. And this is just a different type of manifestation of the steric profile. So it's the same trend from in the trialkyl to primary amines. The smaller they are, the better they are at this displacement reaction. Pyridine is very good, despite the fact that it's not a very strong base compared to these aliphatic amines and phosphines, but it's flat. So we think that's why it helps this equilibrium. And a proposal for that is that, or an explanation for that turns out to be that the equilibrium constant for this reaction is influenced not only by ligands binding to cadmium in solution when they displace, but also ligands bind to the underlying particle surface that's revealed. And it turns out that steric effects are very important for ligand packing and ligand binding to surfaces, as we'll see in just a few slides here. All right, so we're going to just shift gears now. That was about Z-type and X-type ligand exchange. Let's talk for a moment about these neutral donors and this steric effect. And I'm going to first mention the preparation of a material that we'll discuss, starting again from these carboxylate terminated particles. If you can use reagents like chlorotrimethylsilane to cleave off the carboxylates, producing these trimethylsilyl esters of carboxylic acid ligands. And upon exchanging the cadmium oxygen for cadmium chlorine bond and producing this byproduct, now the particles become insoluble because you've cleaved off the organic material that is helping them to disperse. But if you do that exchange in the presence of a phosphine ligand, the product is soluble. And so you end up with a tributyl phosphine ligand binding an underlying cadmium selenide crystal that has some cadmium chloride adsorbed to its surface, and this can be handled like any other colloidal dispersion of nanocrystals that we work with. Now, this phosphorus nucleus in the product is really useful for doing NMR spectroscopy. Phosphorus 31 is a powerful NMR nucleus. It's very sensitive. It has a big chemical shift range. And that makes it useful for quite a bit of coordination chemistry studies in the literature. This particular study I'm going to tell you about is a competitive binding type of a study where various ligands, like primary amines, have been added to these phosphine-bound particles. And by adding primary amines and displacing the tributyl phosphine that was there to begin with, you can study the competition. And that's readily observed with phosphorus NMR. So here's the starting nanocrystal with phosphine ligands bound. And then as you titrate in increasing amounts of primary amines, you can watch this signal go away for the bound phosphorus, and you can watch a new signal appear. And this new signal, in the end, matches the chemical shift of free tributylphosphine. And at intermediate concentrations, you see some interesting broadening and shifting, the origins of which I'm not going to get into in any kind of detail, but probably result from dynamic exchange of ligands on the NMR timescale. In any case, it's relatively straightforward to estimate this equilibrium here, the magnitude of it, and to study which kinds of ligands can displace tributylphosphine. And so using that technique, a variety of ligands have been surveyed, including the ones shown in this figure here. Two ways of showing the data: pKa of various ligands plotted, and their cone angle. I'm sorry I have not included a definition of cone angle here, but it is a metric for assessing the size of something. And it's basically, if you take a cone from a metal to which a ligand that is bound, and you make the cone fit tightly around that ligand, a small ligand will have a narrower cone around it, and a really big ligand will have a wider cone. The cone angle tells you about the ligand size. And so basically, then we looked at those two parameters and found that molecules with a very high pKa of the conjugate acid of these things, or in other words, strong bases, are better ligands, and those with small cone angles or small steric sizes are better ligands. All the effective binders appeared down here, and all of these did not compete very well. Shown on the right are the relative binding affinities. Affinity goes up as you go to the right in this box. For several different classes of molecules, and then a bunch of others that did not compete with tributylphosphine at all. And you'll see some of the same features that we saw earlier in the cadmium carboxylate displacement. Ligands that are sterically small and basic work the best, as I mentioned. Tributylamine does not compete with tributylphosphine. Dimethyl and butylamine does. So does dibutylamine, and then N-butylamine, the primary amine, proves to be most effective. Also, in this series of trialkyl phosphines, going from butyl to ethyl to methyl has a measurable, a large measurable impact on the competition. And then again, down here, we see some weaker bases that still bind. In the case of imidazole and pyridine, presumably that's because of their small steric size, the fact that they're flat. Now, a few that barely make the list: isocyanides, not bulky at all, but also not very strong bases. Consider the pKa of this conjugate base is very low. Thiophene, relatively, it does show some coordinating power, and that's largely because of how soft the phosphorus is. Selenium would also work pretty well here. If you could get a selenium into one of these tetrahydroselenophene, I'm sure is a vile smelling compound, but might be an interesting ligand for a particle. So increasing the size of the molecule has a dramatic impact on the binding affinity. Small molecules bind better than large ones do. And one of the ways you can understand that steric effect is in terms of the coverage of molecules on the particle. So here are three different case studies where we have these simple molecules: tributylphosphine, dimethyl, N-butylphosphine, and then N-butylamine. And if you look at these, if you make these materials and isolate them, you'll find the coverage of ligands varies pretty dramatically between these various molecules. So tributylphosphine and dimethyl N-butylphosphine, the phosphorus cadmium bond dissociation energy is probably about the same. within a couple percent or something like that. But you get 4 times more ligands around the particle if you have methyl groups instead of 2 butyl groups. And that is a direct consequence of steric size. And again, if you switch from the trialkyl phosphine to the primary amine, look at the coverage of amines goes up by another 50 to 100% or so. Okay, and so this change in coverage, if you consider the equilibrium between these two molecules, you get twice the number of connections here, or 4 times the number of connections. And what that means is that dimethyl and butyl phosphine is going to way outcompete tributyl phosphine for the particle surface, despite the fact that the cadmium phosphorus bond association energies are not really going to be that different at all. So this equilibrium constant is less about bond association energy and more about numbers of ligands that can fit. Small molecules pack better than large ones do, and that means that they bind better. So small molecules with a weaker bond association energy can displace larger molecules with a stronger bond association energy for these reasons. So again, we looked at this equilibrium before, and we think that that same sort of a thing can explain why pyridine is relatively good at this reaction compared to a trialkyl phosphine. It's not a very strong base by comparison, but it's small. And so this equilibrium becomes facile because you can put a lot more pyridine around the product than tributylamine or than tributyl phosphine. So that's why I thought pyridine is better at this displacement reaction. Okay, so let's take a look for a moment at the surface facets of a zinc blende semiconductor to kind of help drive this home. Zinc blende semiconductors, the binary semiconductors, show 2 different types of facets. In the sort of simplest case, you have 111 and 100. These are some low energy facets that are thought to be found and lead to cube octahedra. The 111 surface of these crystals is all cadmium or all selenium terminated. And those atoms make 3 bonds to the underlying crystal. You get this hexagonal looking arrangement of atoms, and those orange atoms, which have 1 dangling bond perpendicular to the surface, make 3 connections to their adjacent green atoms beneath, and so on and so forth. So this 111 surface has a single bond that is orthogonal to that plane, just sticking up in parallel across that facet. Now the 100 surface is a perhaps more interesting surface. The atoms here make 2 bonds to the underlying crystal, and they have 2 bonds missing. So here are a bunch of green atoms sitting atop adjacent orange atoms that make 1 connection to each in this nice line, zigzagging along. And then they have dangling bonds in the other direction, pointing at one another. So if you consider ligand binding to these surfaces and where those ligands might possibly sit, you might find that, or you will find that the binding of ligands will depend upon the facets. So binding to a 100 surface might be much stronger than to a 111 surface because the electrostatic potential is higher. There are 2 dangling bonds missing, and so there's a lot more positive charge exposed on that 100 surface than on the 111 surface. And in principle, you could cover all of those atoms with ligands. If you count the number of atoms per unit area on those facets, however, you'll find that they're much higher than the typical coverages of ligands that you find in solution. So the surface atom densities might be something like 6 per nanometer squared, whereas the number of ligands might be 3 per nanometer squared or less in the other examples I showed you. Remember, the tributyl phosphine is 0.5 ligands per nanometer squared. So a huge range, and most crystals of this type, the atoms on their surfaces show a lot of dangling bond character. You know, there's nowhere near coordinative saturation of the atoms on the underlying surface, which is really interesting from a coordination chemistry perspective, to have lots of vacancies and open coordination sites. And it turns out that they can't be accessed for steric reasons. Okay, so I've plotted here surface atom densities for these two facets, 111 and 100, for many different crystals that have the same type of a crystal structure. Zinc chalcogenides, cadmium chalcogenides, the 3,5s. I've also included diamond and silicon and germanium because they also share this type of structure. In their case, there's only a single atom, so it's just the diamond structure, but it's also a cubic crystal structure and has the same facets. So the surface atom densities of those types of facets are plotted on this graph. And you know, as you expect, the bigger the atoms in the crystal, the less densely packed the surface atoms are. But perhaps surprisingly, or I certainly found it surprising, that all of these materials, or almost all of these materials, except for the very largest largest atoms, say cadmium telluride or indium antinomide, all of these materials, the atom densities are much higher than the alkane chain packing density. So if you have a crystal of straight alkane chains, you'll find that their packing density is not as high as the surface atoms beneath. Okay, a diamond crystal is a really interesting example of this because the surface atoms in diamond are 3 times more densely packed than you can pack alkane chains. So if you have one alkane chain standing up on a diamond surface, there are 3 carbons that fit underneath it. So there's quite a bit of coordinative unsaturation on any of these surfaces if organic ligands are the only way to passivate those empty sites. Okay, and what this means is that surface atom density and ligand coverage are very tightly linked, and ligand coverage is limited by steric effects. So small ligands are better than big ligands for that reason. Okay, so let's change gears here and talk a little bit about adsorbed ion pairs. There are many examples of this type of thing in the literature. Here's an ammonium thiocyanate coordinated to a particle, or an ammonium halide. There are also cases where the addition of bases, primary amines being a common one, to an underlying surface can result in deprotonation chemistry. So you deprotonate a carboxylate and the carboxylate binds. You could deprotonate this hydrogen, for example, and obtain an ammonium chloride adsorption. So adsorption of ion pairs is a common motif in surface chemistry, and it's often quite difficult to identify in the materials you're working with. So let me just check the time here. Okay. So an example of this is if you take this sample of carboxylate terminated particles and you add a primary amine to it, you can displace cadmium carboxylate from the surface. But in the end, you can't get rid of all the carboxylate because a small fraction of it has some associated hydrogen that is then bound to the product amine and gives you this adsorbed ion pair. Okay, and so you can remove most cadmium, but not all carboxylate because of the formation of these ion pairs. And another good example of the same kind of reactivity here, again, looking at this chlorotrimethylsilane reaction, we're cleaving off the TMS carboxylate ester. But this material might have some acidic hydrogen present in it. And if it does, you can make phosphonium chloride. So now instead of a phosphine bound, you have a protonated phosphine and the chloride counteranion balancing charge with it. You also have some chloride balancing charge with excess cadmium. And so if you look at these various species here in this product, it can be difficult to tell them apart. A phosphine versus a phosphonium might be sort of intuitive to think about, but uh, it's not necessarily straightforward to be able to see that kind of a difference. Phosphorus NMR is uniquely powerful in this sense because the phosphonium chemical shift stands out from the bound phosphine chemical shift, which is here. Now, if this were a nitrogen, you'd be in trouble. And knowing that you had an ammonium salt versus an amine that's coordinated might not be possible with standard techniques. And so, this kind of thing happens and can be difficult to detect. I think for the sake of time, I'm not going to spend time talking about this piece, but um, if one makes a sample of particles that has amine ligands on it, using a purified source of nanocrystals and removing all of the cadmium salts carefully, in the end, you have this sort of canonical structure that people have talked about for years, where the primary amine ligands bind and stabilize a neutral colloidal particle. It turns out that this material is relatively unstable to aggregation. It becomes a challenge to maintain this material soluble or dispersed in solution unless you keep the amine concentration high. So you have to keep a sample like this in a solution of donor, whereas in say, the starting cadmium carboxylate particles, they're perfectly stable because the ligands aren't coming on and off. They're just sort of stuck. But the primary amines seem to be coming on and off. And that lability makes them susceptible to attachment and aggregation. Interestingly, material like this, let's skip that piece here. Material like this does a series of reactions that might be challenging to see, one of which is that they react with acid. So if you add carboxylic acid to this material, you can obtain this ion pair adsorbed to the surface of the particle. So by deprotonation of that acidic hydrogen, you get this salt. And then it turns out it's difficult to distinguish this from this. And one of the ways you can do it is by hunting for the infrared vibrational resonance of this ammonium ion, which happens to fall beneath all of the aliphatic resonances of the organic ligands, but is nonetheless there. Phosphorus NMR makes this relatively easy because you can see the nice broad signals of the adsorbed phosphonate anions. And then last is another tricky reaction that most people are kind of unaware of. Primary amines react with carbon dioxide to make ammonium carbamates. Bottles of primary amine accumulate this ammonium carbamate salt on their threads, which is that white crusty powder. And for a sample of particles that only has these primary amine ligands bound, CO2 can dissolve in that solution and form these ion pairs that then coordinate to the particle. And this particular example used carbon labeled, C13 labeled CO2 to demonstrate how adsorption of the C13 label gives rise to this broadening of the coordinated carbamate salt. All right, so in a displacement equilibrium, there's some tricky stuff going on. If you add a primary amine to a sample of nanocrystals with metal carboxylate salts that also has carboxylic acid present, you can displace the metal carboxylate as an amine complex, but you can also form these ammonium carbamate salts that adsorb to the particle. Now you might think, all right, well, maybe the amine can also displace the ammonium carboxylate and just make the amine bound sample again. That does not appear to happen, presumably because the ammonium carboxylate is a better ligand for the particle than a primary amine is. And as a result, this kind of a reaction becomes vexing because it's difficult to know that you have something like this versus some metal carboxylate. It's not easy to know that the counter ion is this ammonium ion and not some amine that's bound instead of, say, metal carboxylate. So differentiating between these various cases turns out to be difficult to do with precision. All right, so just briefly here before we transition into synthesis for next time, I wanted to leave you with this picture of the 100 facet of cadmium selenide or any zinc blende semiconductor, where you have cadmium ions that make 2 bonds to the underlying crystal and then 2 dangling bonds that are perpendicular to that plane. And a carboxylate, it turns out, snaps right into place between those 2 cadmium ions where one of the oxygens bridges nicely while the other one just chelates. And what that means is that you actually make 3 bonds to the underlying crystal for each carboxylate ligand. And remember that ligand packing effects are very important because of all the steric properties that limit the coordination ability. And this type of a ligand, because it makes 3 connections per aliphatic chain, the coordinating power of a carboxylate ought to be much higher than of an amine. Okay, an amine on the analogous surface can only make 1 connection to the cadmium, and as a result is not going to stabilize that facet and not going to have the same sort of binding potential. The result also is that on the surfaces of these particles, this 100 facet tends to be better for coordination of carboxylates than the 111 facet. And here is a molecular dynamics simulation that verifies that type of a situation. Carboxylates tend to cluster on particular facets over others, depending upon whether or not the binding is more favored. And this can lead to some really interesting shape control effects. We'll talk about nanoplatelets next time. Where's my cursor? Sorry, we'll talk about nanoplatelets. Down here is a drawing of one such platelet where you have a crystal that is atomically thin, but very wide in the other dimensions. And it turns out that the formation of that material is driven by the stabilization of the 100 facets afforded by carboxylate ligands. And it turns out that very small ligands make that possible. Small ligands pack in high density, and they favor the 100 facet and lead to a thermodynamic preference for that type of a facet and that type of a shape. Okay, so some conclusions from today. A question here. Salvador asks if you can make the platelet large. You can. Compared to the thickness direction, you can get 100 nanometers, 200 nanometers before the material kind of becomes difficult to work with. Whereas the thickness is really only a couple of atoms. So you can make very anisotropic structures that way. Okay, so 2 ways to obtain a colloidal dispersion, electrostatic effects and steric effects, both important. In the case of the electrostatic effects, the zeta potential is crucial. And if you have high zeta potential and low ionic strength in the solution, you get nice stable colloidal dispersions. The type of ligands that bind particles depends upon the nanocrystal stoichiometry. When you think about a nanoparticle ligand complex, you must balance charge. You cannot put charge in a bottle without paying a huge energetic penalty. So charge neutrality is a very, very powerful force in all of science, and also in the chemistry of nanoparticles. You better be thinking about the formula as a whole and ensuring that your structures achieve a charge neutral composition. If metal ions are in excess, bound to the surface of the particle, as we discussed, ligand anions will balance the charges of those. Sometimes ligand anions are balancing charge with an outer sphere cation. NMR is really powerful. NMR spectroscopy is very powerful for studying ligand binding because of the line widths of bound molecules. You can look at ligand exchange and competitions in the way that we have done, and with careful elemental analysis show that occasionally cations or anions from the crystal lattice will come off the particle during an exchange reaction. Ligand binding strength is not just about a single metal ligand bond, it is about the numbers of ligands, the number of connections that can be made to the nanocrystal surface. So we talked about small versus large ligands and how small ligands pack with higher density and can displace large ones simply because they make more bonds. So this is sort of a strength in numbers type of a situation. The ligand may be a weaker binder on a per ligand basis, but as a whole, the more weakly bound ligands will displace the more strongly bound ligands just by overwhelming it in terms of numbers. This is also true of carboxylates and primary amines. Carboxylates make 3 connections to the underlying crystal, whereas amines make 1 in this example of a 1-0-0 facet coordination. And that makes carboxylates special, and for that reason, they can be difficult to remove. Very important principle is that surface atom packing is more dense than the packing of straight aliphatic chains. And so you can't put an organic ligand on every surface atom. That's true on just about every material out there that I'm aware of. And even cases where you have self-assembled monolayers on gold and chains are packed with near crystalline order, the density is lower than the density of gold atoms on that surface. And then finally, ion pairing can often be hiding beneath, and it can be difficult to detect that you actually have the coordination of a neutral ion pair to the underlying crystal and not some sort of stoichiometry issue that affords the coordination.